Okay, let's unpack this. If you are serious, I mean really serious, about building reliable software in C++A,
Mm-hmm.
then there's one fundamental practice you just have to master:
Unit testing.
unit testing. It is the absolute foundation of quality code. It lets you trust the individual building blocks of your system.
And that trust is precisely our mission today. We're doing a deep dive into how C++ unit testing has evolved, specifically for you, the learner.
Right. We want you to get the core concepts of testing and then see the professional tools that scale with real-world projects.
Hmm. And we're starting with the core philosophy that even makes this possible, the concept of bottom-up design.
It's such a simple but powerful idea. The source material lays it out really well. You take a huge, complex problem.
And you break it down. You chop it up into smaller, manageable subproblems. Each one gets solved by its own independent function.
And the genius there is that these functions become these isolated little units. You can design them, test them, debug them, all on their own.
Completely separate from everything else.
And that is unit testing, right? Checking the logic of that one specific independent function, making sure the smallest piece works perfectly before you stitch it all together.
Exactly. But here's the first C++ reality check. Unlike a lot of modern languages, C++ itself, it doesn't give you a standard library for unit testing.
That's a huge point, so you have to look elsewhere.
You have to. You're turning to third-party frameworks. The big ones are Google Test, or one we'll talk about a lot today, doctest.
But before we get to those big, robust frameworks, every C++ programmer starts in the same place,
Mm-hmm.
with the simplest tool built right into the language:
Nice assert.
a macro.
The venerable assert. Yeah, it comes from the cassert library, and
Right.
it really is your starting point for just basic logic validation. It's quick.
Quick, yes, but also a bit of a blunt instrument. So how does it actually work? I want to focus on what happens when things go wrong.
Okay, so it's a runtime check. It's built around a Boolean expression. You just write assert and give it some condition, like, is my function's result equal to 5?
Using a double equal sign.
Right. If that expression is true, great. The assertion passes, and your program just keeps on running.
But if it's false,
The program immediately halts. It crashes. Right there. It'll tell you the file and the line number where it failed, but that's it. Game over.
that sounds incredibly useful for just catching your own mistakes early on.
Yeah.
Guaranteeing a certain state before you move to the next step.
It is. For that specific purpose, for a developer debugging their own assumptions, it's great. But that immediate halt, that's exactly why assert is completely unsuitable for professional testing.
You mean for methodologies like test-driven development? TDD.
Exactly. You just brought up TDD. Maybe we should define that really quickly.
Yeah, let's do that for anyone who's not familiar.
So TDD is a whole process where you write a failing test first, before you even write the code. Then you write the absolute minimum amount of code to make that test pass. Then you refactor.
And for that cycle to work, you need a system that can run, hundreds of tests?
Yeah.
And just tell you which ones fail.
Exactly. A tool that crashes the entire application on the first failure just completely breaks that workflow. You need your test suite to run through everything and give you a nice, graceful report at the end.
So the abrupt, program-halting nature of assert is its fatal flaw in a
Right.
professional context. It's a development aid, not a real testing tool.
Precisely. And speaking of development aids, there's a huge practical warning in our sources for anyone trying this out right now.
Oh,
The assert macro. It does not work as you'd expect in many modern environments, specifically Jupyter notebooks.
that's a great heads up. So if you're
Ah.
following along with some C++ demos,
Right.
you have to use a standard compiler setup, or you'll be chasing a bug that isn't even there.
You will. Now, there's another limitation. This one hits everybody, from beginners to pros. Floating point numbers.
Ah, yes, the inherent inaccuracy of computer math.
It's critical. C++ represents numbers with decimals in a specific way. Single precision floats are only accurate up to about 7 digits. Doubles give you maybe 15.
So if I run a calculation on my Mac, and you run the exact same one on your Windows machine, the results might be slightly different on the 8th decimal place.
They very well could be. And if you're using a simple to compare them, your test is going to fail.
Even though, for all practical purposes, the answer is correct.
Yes, you could spend hours hunting a bug that's just a tiny floating point deviation. The blunt force of assert can't help you there. It's just true or false.
Okay, so that's the point where assert just isn't enough. We need something smarter.
We need tools that don't crash, that can organize our tests, give us detailed reports, and crucially, handle real-world math gracefully.
And that brings us to the third-party frameworks. You mentioned Google Test, but our sources really highlight one called doctest.
They do. It's highlighted because it's seen as really appealing for learners. It's described as lightweight, super fast, and it has a clean structure.
Easy to pick up.
Very. Especially if you're coming from something like Python's unittest library. You'll feel right at home.
And the setup. I mean, C++ setup can be a real pain. The source says doctest is just a single header file, doctest.h.
That is its killer feature.
Right.
Seriously. There's no big build system configuration, no complex linking. You download one file, you hashtag include doctest.h, and you are ready to write professional grade tests in minutes.
That's incredible. That removes a huge barrier to entry. So once it's included, what does a test actually look like?
The syntax is super clean. You define a test block with test case, and you give it a name in quotes, like testing the add function.
Okay, that makes sense.
And inside that block, instead of assert, you use a macro called check.
So check does the comparison. It's like a smarter assert.
Exactly like a smarter assert. It verifies if an expression is true, but here's the huge difference. If a check fails, doctest logs it, tells you what went wrong, and then it keeps going. It runs the next check and the next test case. It gives you a full report of everything that passed and everything that failed.
That's the graceful failure we were talking about, the thing you need for TDD.
Now let's circle back to that floating point problem. How does a real framework like doctest solve it?
Right. This is where the real value comes in, isn't it?
It is. Instead of that flaky comparison, doctest gives you a special tool. doctest.approx. So you'd write something like chi_outprox.prox. I see the approx function, but how do you tell it how close is close enough?
That's the best part. You can chain a method called .epsilon. Epsilon is your margin of error. So if you write doctest.epsilon 1/6, you're telling the test.
You're saying, I expect this exact value, but anything within 1/millionth of it is still a pass.
Perfect. It's like saying, I expect a gold coin, but if you're off by the weight of a single grain of sand, we're good.
You're building tolerance for that inevitable computational noise right into the test itself.
You are. And that level of control is what separates professional testing from basic debugging. But doctest goes even further with features for organizing large test suites.
Okay, so let's talk about a couple of those. The sources mention fixtures and parameterized tests. What are those? Okay, so think of a fixture as setting the stage for your test. Let's say a bunch of your tests need the same setup, maybe creating a specific object or opening a fake database connection.
Right. You don't want to copy-paste that setup code in every single test.
Exactly. You write that setup code once in a fixture. The framework then automatically runs it before each test that needs it. It keeps your code clean, DRY, don't repeat yourself.
I like that. So what about parameterized tests?
That solves a different problem. Imagine you're testing a function that validates email addresses. You don't want to write 50 different test cases for 50 bad emails.
No, you want one test logic, but you want to run it with 50 different inputs.
That's what a parameterized test does. You define the logic once, and then you provide a list of inputs and expected outcomes. doctest runs the same test over and over with each piece of data, telling you exactly which input failed.
That sounds like doctest is really solving all the organizational headaches that pop up as soon as a project gets even a little bit big.
It is. It provides that whole framework for professional scale, supporting everything from exceptions to logging, which are just vital for maintaining complex systems.
So wrapping this all up for you, the listener, what have we seen here? There are really two distinct paths.
Two main routes, yeah. First, you have the quick, simple, but very limited assert. It's your personal safety net during early development.
But it's too destructive for real testing. And then you have the powerful, lightweight, and professional doctest framework.
And that's your tool for serious, large-scale unit testing, or TDD. It gives you organization, precision, and graceful failure handling.
Mastering this, whichever tool you start with, is really the foundation for designing and debugging functions efficiently. You build confidence right into your code.
You really do. And this brings us back to that critical difference in how they fail. We said assert crashes the whole program. Frameworks like doctest log the failure and carry on.
And that's not just a feature, it's a whole philosophy.
It is. Which leaves an important question for you to think about. As you build bigger systems with lots of moving parts, consider this. What are the broader system implications of a component that abruptly crashes on a non-critical failure versus one that logs the issue, maybe handles an exception, and tries to keep the system running?
It's the difference between something that's just fragile and something that's Truly resilient.
When you're thinking about uptime, resilience, and debugging in a live production environment, that choice has massive consequences.
Definitely something to mull over as you start building out your next test suite.